Probability. So let's take this. That was good. Start that again. I thought there were notes underneath it. That was good. That was useful. Probability. This will come up on the program. We'll start with a few things of our everyday experience. Menu choices in a restaurant. You go into a restaurant and you look at the menu. You'll see that in the starter section, there are 3 choices. In the next section, on the main, you've got 4 choices. And in the final one, you've got 4 choices of dessert. How many different possibilities are there for those? Well, let's assume there's no vegetarian requirements, nothing vegan, nothing that you don't want to go with this or that or the other. There's no rules. Absolute free for all. You can pick any one of the starters, any one of the mains, and any one of the desserts. This can go with any one of them, or not. Shouldn't have done that. Sorry about that. Forgot to turn off my own phone. Here we go again. Rewind. Probability. Let's start with question on how many options there are. Let's look at menu choices. You go into a restaurant and there's choice in the menu of 3 starters, 4 mains and 4 desserts. How many different combinations are there? Well, if you look at it, this is quite unrestricted. You can choose any one of the starters. And if you choose starter 1, you can choose main 4 or main 3. With starter 2, you can choose any of the mains. And equally, regardless of where you've been to here, you can choose any of the others. So we might show that in a tree diagram and say you go into the menu, into the restaurant here, and you have starter 1, starter 2, and starter 3. So there are 3 possible choices for you as you go in. As soon as you go in, you can choose menu 1, 2, 3, or 4. And there are your 4 choices in the mains. M1, M2, M3, and M4. And the same for each of the other ones. I won't fill them all in. And well, maybe I will on this occasion. But regardless of what you've had for your starter or for your main, you can then decide, I'm going to have, well, what dessert am I going to have? So just taking this one, I could say I'm going to have dessert 1, 2, 3, or 4. Or here I could say dessert 1, 2, 3, or 4. And I want to imply that that happens for each of the other ones as well in some way. I just expanded up a number of them. But this is 3 options. And by the time it got to here, each of these on their own were sort of 4s. But you had 3 4s. So this became sort of 3 by 4 at that stage. There were 12 options by the time you were in here. And for each of these one, that became a sort of a 4 again, as did this. But there were 12 of those 4s. So this became sort of 3 by 4 by 4. So we can just see the absolute explosive nature of probabilities and combinations and stuff like that. So all we do really in this question is we say it's 3 options here, 4 here, and 4 here. And because any one can be taken with any one by any one, you multiply them. So you can see here that you've got 3 by 4 by 4, which is 48. And what's the chance of a diner choosing a particular lunch? Well, if they're all equally likely, and there are 48 choices, and you're assuming you're going to eat only one of them, one choice, it's 1 out of 48. And that's the answer. That's the probability. So if somebody said, what's the chance of a person coming in and choosing starter 2, main 3, and dessert 1? To say 1 in 48. Now, that's without knowing anything about it. But if this one here is the soup, and this one here is, something like carrot cake, you might say, well, they're not very popular with that age group. They're more likely to go with maybe a salad here, or they might go with maybe something like, I don't know, chicken wings or something. So you'll know from the age profile that people would have totally different starter preferences. But without knowing anything, you'll say, look, it's 1 in 48, roughly. Well, exactly 1 in 48 if we don't know any information. Now I'm going to ask you to consider 2 things, right? Somebody gave you 2 concert tickets. And I know you've got thousands of friends on Facebook, okay? But you've actually got 2 real friends, okay? 2 very close friends. And you've got 2 extra tickets, and you've just been given tickets to a concert that you're screaming to get to. Now, unfortunately, you've 4 very close friends, but only 2 tickets. Now, for simplicity, I'm going to call the friends Adam, Brian, Ciara, and Donna, because it's A, B, C, and D. Is that okay? So you've got 4 friends, A, B, C, and D, who you think about giving the tickets to, and you've 2 tickets. Write out all the possible things you could do. What patterns can you do there? 2 tickets for a concert, what's the answer? So I'm going to work out some of the options. You could give tickets to both A and B. So A, B might be an option. You might give it to A and C, A and D. Or you might leave Adam out entirely and say, what about B and C? B and D. Or you might leave Adam and Brian out entirely and go C and D. If you count up the options, there are 6 different possible options. Only. So this is how we do it. Let's say the names of your friends are Adam, Brian, Ciara, and Donna. And we write the numbers out like that. 2 of them are going to go, and they're the actual opportunities that are there. Is that all right? No more. That's it. Now I'm going to ask you another question. Christmas came around, or your birthday came around, and you were given a few gifts. Somebody gave you a music voucher, and the second gave you a travel voucher. Now, you can't use the travel voucher. Unfortunately, you're not free that time or something like that. And somebody gave you a music voucher. The same 4 people apply. Adam, Brian, Ciara, and Donna. And you've got a music voucher, and you've got a travel voucher. Many ways can you distribute your gifts now. Give that a go. Okay, I'm going to do the question here. Again, I'm going to break it into the 4. And I'm going to say what's possible. Well, AB is possible, AC and AD. You could leave out Adam and do BC, BD, and CD. But also, you could do the following. You could do, remember, what does A and B mean in this case? Well, A and B have a first and a second part here. And I'm assuming that the first one is MV, music video, and the second one is or music voucher, and the second one is travel voucher. Well, if that's the case, you could also have BA, CA, DA, CB, DB, and DC. Let's look at that. What do I mean by that? If you're going to choose Adam and Brian as your two friends to give the things to, you could give Adam the music video and Brian the travel voucher. Or you could swap it around and give Adam the travel voucher and Brian the music voucher. Are they different? Well, they are, yeah, because, I mean, who uses a music voucher nowadays anyway? Where's that going to go? Well, maybe if it's on iTunes, it's fine. But if it's one of these golden discs or HMVs or buying CDs or something like that, maybe there's not a lot of sort of demand as there was for those before. So these are quite different presents. One is a travel voucher that's €200 to go to Paris sometime. And the other is a music voucher that really people are going to download. So really what we're saying here is that this is a different question than the first one, because it matters who gets the first one here. It matters who gets the music and who gets the travel. They're different things. Whereas in the first question, it was just two people going to the concert. Okay, somebody can sit in B18 and somebody else can sit in B17, but it really doesn't matter. They're both going to the concert, the same concert, with the same entitlements. One doesn't have a VIP backstage pass and the other has it. It's not one and the other. They're not different. This is a very important thing you've got to ask yourself in probability. Does it matter the order in which I give these out? Does it matter if I give Brian the music and then Adam the travel and vice versa? If it does, then you're dealing with permutations. If it doesn't matter, you're just saying, combinations, they both get tickets. So in this situation here, if I work it out, I get 12 options. Whereas the last time I did it, with the two concert tickets, I only got 6. So when I worked it all out for the vouchers, for the friends, both where you've got the two different types, you've got the music voucher and the travel voucher, I get 12 outcomes. Because Adam Brian is not the same as Brian Adam. Or Donna Kira is not the same as Kira Donna. If we assume that. Now, do we have to rely on that in our head to figure it out? Well, we could, because we could get it right. But we could also use the formulae, and we know which ones we're looking for. So let's look at a few definitions now in terminology in this whole space of probability. The first symbol you see is this thing, like an exclamation. It is an exclamation mark. It's called factorial. And n factorial is defined as n is n by n minus 1 by n minus 2. Or more simply, 5 is 5 by 4 by 3 by 2 by 1. 3 factorial is 3 by 2 by 1. 7 factorial is 7 by 6 by 5 by 4. You just keep going, really, all the way down, taking one lower integer all the time until you get to 1. And that's what a factorial is. You need that number. It's a useful thing. When I mentioned combinations, you just let two of your friends go to the concert. It doesn't really matter who you gave the ticket to first. Well, I got it first, or she asked me. Don't give any of that stuff. The two of you are going to the concert. So the order is entirely unimportant. In this case, what you're saying is, I am selecting people or objects in any order, and I'm selecting them out of a larger group. And the order doesn't matter. So you've got to figure out is, what was that question about? Really the question came down to this. How many friends did you have? Well, you've loads of friends. But how many friends did you consider for the tickets? You considered 4. How many tickets did you have? You had 2. And did the order matter? Did the arrangement matter? No. Order matter? Matter? No. This was the concert. Really, that's the way that looks. It looked like you have 4 friends, you thought about it, they might be free, you might give them a call, you've only 2 tickets though. This became N. That's the number of friends, N. N is the or, the out of. And this thing here on this occasion says combinations. It doesn't matter whether I give the voucher first or second to this or that. It's just the same ticket. So that's the data we have. So there's a formula for this. And basically it says you can figure it all out on your calculator using a thing called NCR. Sometimes written like this, and sometimes written with the big brackets around it, or sometimes written like this. So the formula says that NCR is equal to n factorial over n minus r factorial or factorial. But of course we have to figure out what the numbers are. Well, we do know the numbers. We know that the number is 4 for n, because that's the total number of friends we had that we considered for the tickets. So that's okay. We know that r is 2. And because it's combinations, that's why we're using the formula with the C in there. So it really becomes 4 people to pick from, C for combinations, 2 for tickets. 4 factorial over, that's n minus r is 4 minus 2 factorial, 2 factorial. Now really it's just numbers. So we say 4 factorial is 4 by 3 by 2 by 1. On the bottom, 4 minus 2 is a bracket, so that's really 2 factorial by 2 factorial. Or doing it all out now, it's 4 by 3 by 2 by 1 over 2 by 1, 2 by 1. And we can start crossing these things out. 2 times 1, 2 times 1, they go. And that 2 there can go into that 4, leaving 2. So in the end, we end up with 6. Or we could have done it this way and said that's 24 on the top, and that's 2 by 2 is 4, and that's 6. So either way, we find that the answer is 6. Is that what we got? That's what we got. When we looked at the concert tickets, we had 4 friends, 4 very close friends. That was our n is 4. We got 2 extra tickets, so that was our r equals 2. And in our own sense, we said, look, they're both going to the same concert. The order doesn't matter. They're not distinguished in any way. One doesn't have VIP backstage pass, etc., so it's C. And 4, C2, gave us 6. And that's what we got. So let's move on. Definitions and terminology. Permutation. Here we're saying the order is important. Here we're saying the arrangement of a number of objects in a definite order is important. Arranging all objects out of a total of n. If the first person item chosen is the music voucher, and the second one is the travel, well then it does matter who gets first. Adam Brian is not the same as Brian Adam. They get a different outcome for it. So here we say, how do we do that? So we say, well, we go back to the question again, and we say, let's look it up if we can. And we say, well, what was the issue? I think we were talking about both the music voucher and the other. Well, let's do the formula first, maybe. The formula here is NPR. Exactly the same type of shape is n factorial over n minus r factorial. How many close friends did we have? 4. It did matter because we had 2 very different presents to give them, so the order was important, so we chose P. And we had 2 friends, 2 things to give, the music and the travel. So 2 to give, that was the R. R is 2, N is 4, and P because it made a difference which one you got. So now we get 4 factorial over 4 minus 2 factorial. And that turns out to be 4 by 3 by 2 by 1 over 4 minus 2. That's 2 factorial. And that's 4 by 3 by 2 by 1 over 2 by 1. And again, we can cancel those. And 4 by 3 gives us 12. Does that make any sense? 12? Is that what we got? Well, this was the example where we had the different presents. We had the music voucher and we had the travel voucher. And that told us in a way that the P, the permutations, was going to be an issue. We still had 4 close friends, which we had before, and we still had the 2. So it was 4P2. That turned out to be 12. And 12 is what we got. So on the next 2 slides, you just see that confirmed without much of the commentary. 4 friends, 2 tickets, it doesn't matter. They're both equally welcome. We say 4C2, either 4C2 this way or 4-2 this way is represented sometimes, or the other formula here, giving us 6. Example 2, same thing. Permutations, 4 friends, 2 gifts. The gifts are different. If you ever see the word different, arranging, they're saying the order is important. How many ways can you arrange things? For example, you have a race and you have 8 runners in a race. There are 3 medals. Is the order important in the medal sequence? Is a gold different from a bronze? Yeah? Whereas sometimes if you go, and I've suffered these, you go to a gala event of, say, swimming or something like that with your children when they're in junior infants, and there's 60 people in the junior infants gala, and they all get a medal because they're all wonderful, right? Or they all get a lollipop because they're all wonderful. And indeed, they are all wonderful. But really what we're saying is the order doesn't really matter much. Is that okay? Would you tell that to anybody who came 4th in the Olympics? Does the order matter? Absolutely it does. So what we're going to do in terms of the questions is you've got to figure out, is there a hint in there? And the words they put in was, how many ways can this be arranged? So let's say, for example, just talking about that while we're on the arrangement. You're in school, and it's a coeducational school, so you have boys and girls, and there's an election in your class. And for the class election, they want to pick 4 members from your class. They want to pick 2 girls and 2 boys. What you can do there is you can say, this is a class, 30 people. And for the moment, I'm going to say that there are 14 girls and there are 16 boys in this particular class. And I want to set up a committee here with 4 people to represent the interests of the class. But I want 2 of them to be for girls and 2 of them to be for boys. Is that okay? So out of the 14 girls, I want to choose, I want them to be elected, or they have to choose, or they have to decide, 2 of them, and these have to decide to choose 2 as well. 2 to choose from each of those. Now, does the order matter there or not? Before you answer that, just think of this. As long as Mary and, Joanne get on the committee, it doesn't really matter who gets on first. But just turn this committee for a second, and let's say that this is the head girl, or the class rep, and this is the secretary, or the sports officer, or the vice president, or whatever. This is the head girl, and this is the deputy. Head and deputy. Now you're saying, hold on a sec, this is different. So once you start talking about electing people to a committee, where you're saying there's the president, the treasurer, the accounts officer, the whatever, then you're saying, hold on a sec, the order matters here. Is that okay? And that's the common sense in English coming through. That's where in the project maths you're reading and you say, what's really going on here? Does it matter? No. In the first case it didn't matter. There were 2 tickets for a concert. They both got in. No big deal. In the first case here, it's just a committee. 2 get elected. Great. 2 get elected and 1 has to be head and the other not head. Ah, well, now, hold on a sec. That's different. I have to figure that one out. So it's just keeping your normal common sense antenna open. So we'll come back to that. We'll now look at a few probability formulae. And you understand all of these, by the way, all of them. But once we start without the formulae. Probability is given by, the probability of an event is given by the ratio or the fraction of the number of successful outcomes over the number of possible outcomes. So if somebody said to you, what's the probability of getting a 2 on the roll of a die with 6 sides to it? You'd say, well, 1 in 6. Because you'd say, what could happen? I could get a 1, a 2, a 3, a 4, a 5, or a 6. And only one of those is a 2. If I toss a coin and I've got heads and tails, what's the chance of getting tails? Well, it's either this or this, so it's 1 in 2. And the way that's formally written, and it's called the official formula for this, and you might write the sentence of it, is the number of successful outcomes over the number of possible outcomes. So in the dice, it'll be, well, there's 6 possible, 1 of them is a 2, and that's it. There's also another pretty useful formula that says the probability of an event happening plus the probability of an event not happening is 1. So if you're saying, what's the probability of my waking up before, going back to school, what's the probability of my waking up before 7 tomorrow? So I don't know. But the probability of waking up before 7 plus the probability of you not waking up before 7 has to add to 1. Because something's going to happen. You're either going to wake up or not wake up before 7. There's no other possibilities. Now, you might have a 50-50 chance of waking up. You might be somebody who wakes fierce early and you might have a 95% chance of waking up. Or you might be somebody that has to be dragged tomorrow because you're exhausted or whatever. And you might have only a 1% chance. Or 1 in a million likelihood. But if you add the two together, the likelihood of you waking up or not waking up, they have to add to 1, because something's going to happen. That's for sure. The word "and" makes life more difficult in probability. And more difficult means the probability gets smaller. So you say the chance of you winning the lotto is that you have to get the first number that you tick on your card right, and the second one, and the third, and the fourth. So as you go through all of these ands, it's getting more difficult. The chance of you winning the X factor is the probability that you have an excellent voice and talent, and you can get on the show, and you don't make a mess at the time, and the judges particularly like you, and. So as the probability increases with all these stages of ands, life generally doesn't get much easier. The word or generally makes things easier. Won't make things harder, but it usually makes things easier. So if somebody said, look, you can win on the X Factor if you've got a great voice, or if you happen to know one of the judges, or if your mother or father happens to be somebody famous like, or, and all of those ors are helping a little bit along the way. So the probability increases. So I'm going to take an example that you're familiar with, and I'm going to do a lot of these questions on it. I'm going to imagine that you're rolling a die, and a die has 6 sides, and it's got 1, 2, 3, 4, 5, and 6. So when I roll this thing, I'll get one of those numbers, and they're all equally likely. That's a 6th chance, 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 a 6th chance. That's the probability that I get a 1. What I want you to do now is I want you to work out the following questions without using any formula. What's the probability of getting a 1 on the roll of a die? What's the probability of getting an even number, an odd number, an even number or a 1, an odd number or a 1? So just take a few moments and just do that, please. Okay, let's turn to this question. I'm going to write down the 6 options. So you're rolling this dice and you can get a 1, 2, 3, 4, 5, and 6. The first question is, what's the probability of getting a 1? So the probability of getting a 1, we just leave those to the one side. They're the options that you can get. Maybe move it to there. Now, the probability of 1, well, there's only one option of getting a 1. There's 1 there, but there's 6 in total. The equation says the probability of the number of successful events, that's one of them, over the total number of events is 6. So that's the probability of getting a 1. What's the probability of an even number? Well, when we start looking at even numbers, we note that 2 is an even number, 4 is an even number, and 6 is an even number. So we say there are actually 3 conditions here, 3 events that satisfy a successful outcome. They'd be even. But there's 6 in total, so that'll be 3 over 6 or 1 over 2. What's the probability of an odd number? Well, an odd number here would be, well, 1 is an odd number, 3 is an odd number, and 5 is an odd number. So there's 3 of them that meet the condition, and 6 in total. And that gives us 1 over 2 again. Now, the next one is an even number or a 1. P even or 1. Well, P even or 1, this is even, that's even, and that's a 1. So there are 4 of them that meet the condition over the 6. So that would be 2/3. And now, the last one, we might go with, say, red. We might say, what's the probability of odd or 1? Well, if we start looking at odd now, we say, well, 1 is odd. 3 is odd. 5 is odd. 1 is odd. Sorry, we already had 1 is odd. Saying it twice doesn't add to it. We could say it 1,000,000 times. We've counted it. It's still 3 over 6, which is a half. So, if we look at this, we say that the probability of 1 in the roll of a dice is a 1/6. Even number, 3/6. Odd numbers, 3/6. Even number or 1, 4/6. Odd number or 1, 3/6. Useful to look at that for the moment. What we found was that this word here, or, even or 1, added the 3 over 6 to the 1 over 6, because it took the even number here of even, was 3 over 6, 1 was 1 over 6, and for some reason P even or 1 was 4 over 6, because all we did was we added this to this, so 3/6 and 1/6 gave us the 4/6. But when we use the same logic here for or, and we said P odd or 1, well, the odd would have been, P odd would be 3 over 6. P1 is 1 over 6. But P odd or 1 was still 3 over 6, because there were still only 3 numbers there, 1, 3, and 5. So this or didn't help us here. We already counted it. So or doesn't always make life better. It'll never make it worse. Okay? But it won't always necessarily make it adding. So let's go with that, and let's look at sample spaces. And we say, write down all possible outcomes now for an event from a number of related events. Toss a coin. So we've got heads and tails. Roll a die. 1, 2, 3, 4, 5, and 6. And I want you to write out the sample spaces for that, please. So we'll return to this. We'll toss a coin, and the sample space would be H, comma, T. It's the full space. It's either a head or a tail. Rolling a dice, it's 1, 2, 3, 4, 5, or 6. And tossing a coin and rolling a dice, remember that we'll keep the order importance, tossing it and rolling. If we're putting it in order, let's say in that order, we would say the tossing of the coin can give us a head, followed by a 1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, and T6. If the order does matter, and we say, it depends on which one you use first, and we're considering that, we could also include 1H, 2H, 3H, 4H, 5H, and 6H, and also 1T, 2T, 3T, 4T, 5T, 6T. Depends on whether the order is important or not. Now, I'm going to give a question here, and write down all possible combinations of outcomes from an event or from a few related events. You've got a 2-course lunch with a choice of 3 starters and 4 main course lunches. How many different combinations are there in total? So I'd like you to write down the actual choices you have there, assuming that you've got S1, S2, and S3 for your starter, and you have main 1, main 2, main 3, and main 4. So give that a go, please. Write out the sample space for it. So we turn now to trying that. We've got S123 and M1234. We could see that as a tree diagram, if that helps it visually to get the picture there. For each of the starters, we can use any of the 4 mains. One isn't precluded by the other. We fill in all the others as well. So it looks like we've got 3 choices here, and for each of those we've got a 4 and a 4 and a 4. So that'll be 3 times 4, or 12 choices in total. So we write that out in a sample space by taking the S1, sorry about that, we'll take S1, S1M1, S1M2, S1M3, S1M4, S2M1, S2M2. I'm just going through each of these, S2M1, M2, M3. So I'm going through each of the combinations, M3, S2, M4. S3, M1, S3, M2, S3, M3, and S3, M4. I'm assuming that I'm eating the starter first before the main, but it actually says how many different combinations are there. And because it's combinations, really what they're saying is S1, M1 is a combination. It's a starter one with main one. If you choose to eat them in a different order, that's fine. It's still a combination. You still chose starter one and main one. So you don't have to worry about M1, S1 as being different, because it's not different. It's the same combination. You chose, these are the two things you chose. Had they chosen to use the word permutation and what order and stuff, that might be different. It would be different. But that's the set. So now let's look at practical questions. And these come about forming committees. Here we have a situation where we have 5 girls and 4 boys are members of a social group, badminton, whatever. They're in some society, archery, whatever they're into, right? Music. 5 girls and 4 boys. And they're members of the same social group. They wish to appoint a committee of 4 people, a committee of 4, to organise. How many ways can the committee be formed? So there are 5 girls and 4 boys. And they wish to set up a committee with 4 people on it. In other words, there's girl 1, G1, G2, G3, G4, and G5. And you have B1, B2, B3, and B4. How many ways can you set up that committee? So I'll leave that with you for a moment. See if you can work out the following. I want you to work out the following questions. 1, what's OR? What's N? Is order important? So we've got a situation, 5 girls, 4 boys, figure it out. Give it a go. Thank you. So I'm going to return now to do the question. There are 5 girls. There are 4 boys. And I want a committee with 4 people on it. But if I just want a committee with 4 people, 5 girls and 4 boys, it doesn't say anything about having to have girls on the committee or having to have boys on the committee. There's absolutely no restriction. I could have all of them girls or all of them boys or any combination. So in a way, this is just distraction, really. Because I can pick the 4 people from any of the group, I can see this as 9 students or 9 people. And 4 on committee. I don't have to worry if there's no restriction about boys or girls. They're just people in the group. So the total number of people in the group then is therefore 9. How many do I want on the committee? I want 4 on the committee. Does it matter? Is there a president, a vice president? Not that I know of. If you're on the committee, you're on the committee. So it's a combination question. So if it's a combination question, which it is, and I want 4 of them, and there's 9 people in total, the answer is 9C4. And I just write that down, whatever that is. 9 factorial, 9 by 8, by 7, by 6, by 5, by 4, by etc. Or more simply, 9C4, 9 factorial over 4. Well, we look up the formula. So let's go for that formula. We're saying that the answer is 9C4. Okay, so it's 9C4. Well, let's go to the tables now and says, what does 9C4 mean? Well, the formula for C is that it's, well, NCR first, is n factorial over n minus r factorial, or factorial. We have our table that says that n is 9, that r is 4. So we should now be able to plug in the numbers into the equation. So 9 would be 9 factorial. And this would be on the bottom, 9 minus 4 factorial by 4 factorial. So that's going to be on the top, 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1. 9 minus 4 is really 5 factorial by 4 factorial. And what is 5 factorial? I was writing it out longhand, but really 5 factorial is 5 by 4 by 3 by 2 by 1. And that means that all of that takes out all of that. So we're left with then 9 by 8 by 7 by 6 over 4 by 3 by 2 by 1. We say, let's start seeing if we can divide some of these things now. Well, the 2 and the 3 give us 6. The 4 goes into 8 twice. 9 times 2 times 7, whatever that turns out to be, 63 by 2, 126. So there are 126 different ways in which those committees could be formed. So if we put names on the 5 girls and names on the 4 boys, we could work out 126 different combinations of 4 different names from the class on that committee. Before we even began to talk about who got president or who got vice president or captain or coach or whatever the social group would be, lead singer or whatever it would be. So that's the C there. And there we see the calculations. We see it breaking down to spotting that the 5 and the 4 didn't matter, that was really 9 people. Knowing that we needed 4 in the group, that was our R, and this was our N. And knowing that it was a committee, so it's 9C4, 126. More complicated question now. If the committee is required to have at least 1 girl and at least 1 boy, then the 4 girls option and the 4 boys option must be excluded. So how do you figure that one out? You've got to rule out the option of having 4 girls and rule out the option of having 4 boys. Well, I'm going to ask you a question here. Think of it this way. If there are 5 girls to choose from, and your committee is 4 people, how many ways can you get 4 girls on the committee? Let's assume there's no restriction. How many different ways can you get 5 from the 5 girls? How many ways can you choose 4 of them? Let's give them names. Alice, Barbara, Clodagh, Dervla, and, I don't know, Esme. Okay? I know an Esme, she works here. She's a delightful lady in our music school. Okay? But let's imagine A, B, C, D, and E, right? Now, how many ways can I populate this with 4 of them? Well, we can work it out. We can say it's a combination question. There are 5 of them, and I want 4. So it's 5C4. So it's 5 factorial over 5 minus 4 factorial, 4 factorial. That's 5 factorial over 1 factorial, 4 factorial. If we work that out, we can say that it's 5 by 4 by 3 by 2 by 1 over 1 by 4 by 3 by 2 by 1. That solves that problem for us. The 1 goes into 5 times. It says there are 5 ways. And actually that shouldn't surprise us, because if we were putting the group together and we could only pick 4 of them, these are the 5 things that can happen. You either leave out Alice, or you leave out Barbara, or Clodagh, or Dervla, or Esme. That's the 5 ways. Because they're all different. If Esme's not on it, it's different from Alice not being on it. Different from Clodagh not being on it. All those various things. So that's the way that works. So there's 5 ways. How many ways are there for the boys? Well, there's only 4 boys and 4 in the committee. How many ways can you manage that? You've got Adam, Brian, Connor, and Dermot. Many ways can you put 4 boys on the committee? Only one way. They all have to go on it. Now, if you use the calculator, you'd say 4C4, which is 4 factorial over 4 minus 4 factorial, 4 factorial. That's 4 factorial over 0 factorial, which, by the way, is defined as 1. So is 1 factorial 1 times 4 factorial. That's 4 by 3 by 2 by 1 over 4 by 3 by 2 by 1. And they have quite a similarity, really, because it's just 1. There's one way of putting the 4 on it. So really what they're saying is that for you to solve this way, if they say, look, you can set up your committee, there's 5 girls, 4 boys. We want 4 people. We don't want them all to be girls or all to be boys. After that, I don't mind. You can have 3 boys or 3 girls or whatever, I don't mind, but don't make them all. Well, what we did there was we said that in the first case we said there were 9 people, we wanted 4, that gave us 126 options. That was if there was no restriction. No restriction. For the girls, there were 5C4, 5 ways with all girls. And so not really gone on that. And then 5C4, 4C4 for the boys, 4C4 is 1 way for all boys. So this was 126 minus 5 minus 1. There's 120 ways now in which that committee can be set up so that you've at least got 1 boy on it or at least got 1 girl on it. And that's how you do it. We'll finish this by saying, what would happen if they said, look, set up the committee, but will you please put 2 of each on it? 2 boys and 2 girls. There were 4 boys, or there are 4 boys to choose from, and there are 5 girls to choose from. But this relates to the committee And this relates to the group overall. So the question is now, how many committees? How many committee patterns can you work out? So leave that with you for a minute. How would you work that out? How many ways can you get the two girls you need? If you want two girls, how many ways can you get the two boys? And how many ways overall? Well, returning to this question, I'm going to look at the boys. How many boys are there? 4. 4 must relate to n. How many do I want in the committee? How many boys do I want? 2. Does it matter about the order? No. Because there's no president, vice president stuff. On the girls, there are 5 girls. The order doesn't matter, and I want 2 of them on the committee. So I've got 4 factorial, 2 factorial, 4 minus 2 factorial, 5 factorial, 5 minus 2 factorial, 2 factorial. So in terms of the boys, I've got 4, which is 4 by 3 by 2 by 1, over 2 by 1, 2 by 1. That's the boys. And for the girls, I've got 5 factorial, 5 by 4 by 3 by 2 by 1. 5 minus 2 is 3, so that's 3 by 2 by 1, by 2 by 1. Again, I have a lot of cancelling that I can do here. The 3 by 2 by 3 by 2. Then the 2, if I do the last bit of cancelling here, and I can say, okay, where are we? The 2, it goes into the, well, what I've got is 4 by 3 over 2, and I've got 5 by 4 over 2. 4 by 3 is 12 over 2, and here I've got 20 over 2. I've got 6 times 10. There are 6 ways I can get the boys, the 2 boys, and 10 ways I can get the girls. Do I then say 6 plus 10? No, I say 6 times 10, 60 ways. Because if you think about it, if I've chosen 2 boys, and let's say they're Adam and Brian, that doesn't in any way restrict my choice of the girls. It's like the starter. I can have any main course I like in that sense. So it's the multiplication. Similarly, if I've chosen 2 of the girls, it doesn't restrict in any way my choice of the boys. So these are completely independent. We multiply, so we've 60 ways. So if you wanted, you could work out for this committee, just from your own calculations, you could say 4 girls, 3 girls, 2 girls, 1 girl, no girl. Add up the 5 of those options, and they have to add to 1. If there's 126 options entirely, they have to be counted, because you'll either have no girl, or 1 girl, or 2 girls, or 3 girls, or 4 girls. There's no other possibility. So they all have to add to 1. 126 of the 126 items have to be counted for. I've got The section finished, but I just want to stay on track and just show you something that would have been useful if they showed you this along the way. It's an interesting insight into probability. I'm sure at some stage in your life you were asked to multiply x plus y by x plus y. Have you seen that ever? And you worked it out with the FOIL method and you got x squared plus 2xy plus y squared. And if you had nothing better to do, they might have said x plus y cubed. And they got you x cubed plus 3x squared y plus 3xy squared plus y cubed. And then they said x plus y to the 4. And they started showing you patterns like x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. So you started seeing numbers like 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 1. A Pascal's triangle or something like that. Okay? I believe when they were doing this question, they gave you the wrong question to do. I think they should have given you b plus g cubed. That's b cubed plus 3b squared g plus 3bg squared plus g cubed. And that b plus g squared was b squared plus 2bg plus g squared. That would have made far more sense. Why? Well, the reason is that B stands for a boy and G stands for a girl. And if you're going to have children, B plus G to the 1 is B plus G. If you're going to have one child, you're either going to have a boy or a girl. If you're going to have two children, you're either going to have BB, two boys, GG, two girls, or BG, boy and a girl. If you're going to have three children, you're going to have either three boys, B cubed, three girls, B squared G, two girls and a boy, two boys and a girl, and here two girls and a boy. But far more interesting is that if you start looking at the coefficients here now, and you start wondering, why is that a 2 and that a 3, and all the others presumably just 1s? If you want a boy, there's only one way to have a boy. If you want a girl, there's only one way to have a girl. But in this family here, you've got a boy and a girl. If you'd like to have a boy and a girl, well, if you want to have two boys, there's only one way. Two girls, only one way. But if you want to have a boy and a girl, well, you could have the boy first, couldn't you? And then the girl. Or you could have the girl first and then the boy. There's actually two ways in which that could happen. But there's only one way. If you want two girls, girl, girl. Two boys, boy, boy. Now look at the situation here for 3. If you want 3 boys, boy, 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 that's fine. 3 girls, girl, that's fine. But you want 2 boys and a girl. And lots of you people know people in friends, in families with 2 boys and a girl. But there's 3 ways that can happen. It could be a boy, a girl, a boy, a girl, a boy, or a girl, a boy, a boy. In other words, out of the 3 children, the girl can come first, second, or third. And here, 3b squared g means that the boy could come first, second, or third, because it could be boy, girl, 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 boy, girl, or girl, girl, boy. So out of the 8 possible options for a boy and a girl, if you imagine on every birth you've got a boy or a girl, you have a boy or a girl, boy or a girl. Third birth, boy or a girl, boy or a girl, boy or a girl, boy or a girl. If we write out all the options, this one here is boy, boy, boy. This one here is girl, girl, girl. They're all equally likely, by the way, individually. This is girl, girl, boy. This is boy, boy, girl. This is boy, girl, boy. boy, girl, girl. Girl, boy, boy. Girl, boy, girl. 1, 2, 3, 4, 5, 6, 7, 8. That's right, 8 possibilities. 2 here, 2 each, 2 each. 8 possibilities. So if you look at families with 3 children, there are only 8 possible options. One of them is 3 boys, and that's 1 chance in 8. One of them is 3 girls, 1 chance in 8. Had to be girl, 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 had to be boy, boy, boy. But if you wanted just 1 girl, you can get it here, here, and here. So there are 3 ways of sort of 1 girl. That's your 3/8 there. If you wanted just 1 boy, you'd have to pick this one here with the 1 boy, this one here, and this one here, and link those 3. And that'll be your 3/8. An 8, 3/8, 3/8, and 1/8 gives you your 1, 3, 3, 1. Gives you your 1, 3, 3, 1 in the x plus y. And in fact, if they widen that out to p plus q to the 3, p cubed plus 3p squared q plus 3pq squared plus q cubed, and let's say p was to win something, the probability of winning something, and q was the probability of losing something. If you play a game that has a chance of winning or a chance of losing, it could be any game, it could be rolling a dice, it could be playing somebody in tennis, it could be a match against a friend in FIFA or whatever, doesn't matter. If there's any game where you say I have a chance of winning of P is whatever and a chance of Q is the other, if I do it 3 times, there's 1 way I can win 3 times, 1 way I can lose 3 times, 3 ways I can win twice, 3 ways I can win only once. If, for example, I'm rolling the dice, and the chance of getting a 1 on the roll of a dice is 1 over 6, then the chance of not getting a 1 over a dice is 5 over 6. And if somebody says, what's the chance of rolling a dice twice and getting 2 1s out of 3 rolls? Well, the 3 rolls would say, I've got to do it by 3. The P would say the chance of getting a 1 is a 6th. And if I want to win twice, I have to have the P's here. So I have P squared for the twice winning. 3 is there because it's the 3rd row because I'm going to play the game 3 times. And P is a 6th. So the probability would be 3 times. P would be a 6th. I have to do that twice. Times Q, 5, 6. And that's the way it will be done. But it all goes back to this question here. Why did you do x plus y? You should have done b plus g. There's far more in there. Lovely topic. And that's the end of probability. Thanks a lot. See you after lunch.